Welcome back, everyone. Today we're going to look at Section 9.3, the integral test and p-series. Okay, so the integral test is generally used for positive terms. So say if f is greater than 0, continuous, and decreasing for x at least 1, and a sub n is equal to f of n, and sum from n is 1 to infinity of a sub n, and integral from 1 to infinity f of x dx, either both converge or both diverge. Now this can work for other x's greater than 1. If you remove a finite number of terms, it won't change if the series converges or diverges. So occasionally we'll have to start with x at least 5 or x at least 10. As long as we're just removing a finite number of terms, that's okay. This will still work. Okay, so our first example, look at the sum from n equals 1 to infinity of n over n squared plus a half. So this is positive for n at least 1. So, and if n is at least 1, numerator is positive. Square anything, it's a positive. Positive plus a positive is positive. So this is positive for n at least 1. This is continuous. We're concerned about for n at least 1. This is really continuous everywhere. N squared plus 1 is never equal to 0 in the reals. So the only thing we really need to check for is we have to make sure that this is decreasing, the third one. So what we can do is use a let line, let this temporarily become a function. Let f of x equal x over x squared plus a half. So we're creating an equivalent function, and we're checking to see if this function is increasing, decreasing, or constant for x at least 1. So increasing, decreasing, constant, of course, that's derivative territory. So this is just a quotient rule problem. So derivative of the numerator, keep the denominator, minus keep the numerator, differentiate the denominator over the original denominator squared. So f prime of x, let's see, so we have x squared plus a half minus 2x squared. So that would be a half minus x squared over x squared plus a half quantity squared. Okay, so if x is at least 1, 1 squared, some positive number, that would start us off at 1. Half minus 1 is negative 1/2. That is negative. Anything bigger than that, so 2 squared. 2 squared, 4. Half minus 4, negative up top. Notice the denominator is always going to be a positive. So anything past 1 is negative at the top, positive at the bottom, so this is decreasing. So this does qualify for the test that we're interested in. This qualifies for the integral test. So this was, remember, positive continuous, and decreasing for x at least 1, n at least 1 in the sequence part. So we'll do the integral from 1 to infinity of x over x squared plus a half times dx. If this converges, the original series converges. If this diverges, the original series diverges. So this is just a quick little u substitution, guys. So if u is x squared plus a half, then du is 2x dx. We've got our x dx, so we just need a 2 there. So we have half integral of u underneath a du. So that is half natural log absolute value of u, evaluated from a to b. So that's half natural log absolute value of x squared plus a half. And we're evaluating that from 1 to infinity. So infinity squared plus a half is infinity. Natural log of infinity is still an infinity. Half of infinity is still infinity. So this will diverge. So since this diverges, the series also diverges. So if one of them fails, both of them fails. If one of them makes it, both of them make it. So our next one that we get to play with, we'll look at the sum from n is 1 to infinity of n over e to the n. This is positive for n at least 1. E to the n, e to a power is never worth 0, so this is continuous or n at least 1. Then we just have to check if it is decreasing, so we use our let line again. Let f of x equal x over e to the x. So f prime of x, derivative of the numerator, keep the denominator, minus keep the numerator, differentiate the denominator over the denominator squared. So that's 1 minus x over e to the x is f prime of x. So this is where 0 at x equals 1, and after that everything is negative. So this is decreasing for x greater than 1. So this does qualify for the test. So we'll do the integral from 1 to infinity of the function version of our series. So x over e to the x times dx. And on this one, we can consider this 1 to infinity of x e to the negative x dx. And hopefully you recognize that as being a pretty good candidate for integration by parts. So u here would be x, dv would be e to the minus x times dx. So then du is worth dx. V, we know there's an e to the minus x involved. If I differentiate that, though, I'd have minus e to the minus x. I don't see that. So we'll need a minus sign out there. We'll multiply by -1. So then this is uv minus integral of v times du. So again, a reminder from the previous page, u is x, du is dx, v was minus e to the minus x, and dv was e to the minus x times dx. So uv minus x e to the minus x minus integral of v times du. So minus x e to the minus x plus integral e to the minus x dx, and these are of course from 1 to infinity at the moment. So minus x e to the minus x minus e to the minus x from 1 to infinity. So we have minus x over e to the x minus 1 over e to the x from 1 to infinity. We can write this as a single fraction. And you can see that we'll need L'Hopital's rule here. If we let x go to infinity, we have a minus infinity over infinity. So we'll use L'Hopital. So we'll do the limit as x goes to infinity. This would be the negative 1 over e to the x, which would go to 0. So since that converges to 0, the series converges. Either they both diverge or they both converge. This time they both converge. All right, so our next at bat, our friends, the P series. So from 1 to infinity, 1 over n to the p. So that's 1 over 1 to the p plus 1 over 2 to the p. We're just looking at the moment at the expanded form. So 1 over 3 to the p plus dot, 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 keeps going forever. For p equals 1, this is called the harmonic series. Just a special name it's given. Now a theorem with this, theorem 9.11. Setting the stage, sum n equals 1 to infinity, 1 over n to the p. This will converge if p is greater than 1, diverge if p is on 0, 1, open on 0, closed on 1. The way we can actually prove this, we can show it with integral tests. So 1 over x to the p is the same as x to the minus p. So using the power rule, there's our antiderivative from 1 to infinity. Now I can kind of split this up. Remember, if you're multiplying with the same base, your shortcut was adding the exponents. So then this is really like having an x at the top. So there's that x to the plus 1 power. And then downstairs we have 1 minus p x to the p. So if x is going to infinity, and here again p is greater than 1, I have more x's in the denominator than the numerator, that will go to 0. And then trying out a 1 for the x, 1 over 1 minus p, and then 1 to any power is still just 1. So negative 1 over 1 minus p converges. And we're going to, I should just at least kind of walk you through why we were allowed to use that integral test. So if f of x was 1 over x to the p or x to the minus p, if x is at least 1, then this isn't a 0 in the denominator, so we are continuous. If x is a positive number to a power is still positive, so continuous, positive, and then we would just have to show that this is decreasing. Well, f prime of x would be minus p x to the minus p minus 1, which is minus p over x to the p plus 1. X to the p plus 1 is positive, minus p is negative. Negative or positive, this is decreasing. So it did meet all of our criteria. So p series will converge if p is at least 1, diverge if it's 0 through 1 inclusive. So we have to be bigger than 1 in order to converge. All right, so quick example, putting that to work. So from 1 to infinity of 1 over n. So 1 over 1 plus 1 over 2 plus 1 over 3 plus dot dot dot. So here, p is equal to 1. So by the theorem that p is on 0, 1, this diverges. If instead we're looking at sum from 1 to infinity of 1 over n to the 4th, do a couple terms to show you what that looks like. 1 to any power is 1, 1 over 1 is still 1, 2 to the 4th, 3 to the 4th, 4 to the 4th, etc. So here p is worth 4, p is greater than 1, so this converges. So it doesn't. The theorem doesn't necessarily tell us what it converges to. It just tells us that yes, it will converge. All right. So this next one we'll start this time at 2. So again, remember we are allowed to sort of move things down. If we remove a finite number of terms, we're still allowed to use the same properties. So we have 1 over n natural log of n. We want to see if the series diverges or converges. So clearly not a p-series test. The p-series was just 1 over n to a power. This natural log of n throws things off. So then we'll see if we can use the integral test on this. So look at temporarily f of x is 1 over x natural log of x. So if x is at least, in this case, 2, because they told us n starts at 2, so we're guaranteed x is at least 2. 1 by itself is a positive, x by itself is positive, natural log of 2, natural log of 2 is still, natural log of 2 is still a positive. So we are positive for x at least 2. We're continuous as long as the denominator isn't worth 0. So natural log of x is never worth 0. X by itself is never going to be 0 on the interval that we're talking about. We're starting at 2, so it's continuous. Again, it doesn't have to be continuous everywhere, just where we're looking. And then we just have to see if it's decreasing everywhere. So we need f prime. So f prime of x. So there's a couple ways we can go about this. I'll just take the shorter way. We'll just use the chain rule here. So x natural log of x to the negative first. So f prime negative 1 x natural log x times the derivative of what's inside. So derivative of x is 1. Keep natural log x plus keep the x, differentiate natural log of x. So f prime of x is minus x natural log x times natural log x plus 1. And this is to the negative 2 there, which will just drop that into the denominator. So f prime of x minus natural log x plus 1 over x natural log x quantity squared. Okay, clearly our denominator is positive. Numerator, natural log of x for x at least 2 is positive. Positive plus positive is positive. Opposite of positive is negative. So we have a negative upstairs always, positive downstairs. This is decreasing. And those were the 3 criteria. So we can use the integral test. Positive, continuous, and decreasing on the interval we're talking about. So the integral test can be used. So we'll do the integral from 2 to infinity of 1 over x natural log x times dx. On this one, we can use a little bit of rearranging. Instead of the x in the denominator, we can think of it as 1 over x in the numerator. So u would be the natural log of x. Our du then would be 1 over x times dx, and wouldn't you know it, 1 over x dx there. So then this is the integral from a to b of du upstairs, u downstairs, so that's natural log absolute value of u from a to b. So natural log of x evaluated from 2 to infinity. These really should be in absolute values there. Natural log of infinity is infinity. Natural log of infinity is infinity again. So this will diverge. All right, so from 9(3), I would recommend 1 to 23 odd, 27 through 41 odd, 87 to 97 odd. And I do have a couple of hints that I want to share on those. So on number 7, n squared plus 1 for the denominator. And a little hint on these, 87 to 97, those are a mix from multiple sections. In other words, they're not just going to be exclusively P-series and integral tests. It's going to be a nice little mini review of other stuff as well. All right, so if you have any questions, please Don't hesitate to get in touch with me, and stay safe out there.